So I'd like to introduce Dr. Nadia Sabeh. She's the founder of Dr. Greenhouse Consulting. Dr. Nadia Sabeh is president and founder of Dr. Greenhouse, an agricultural and mechanical engineering firm that specializes in the design of HVAC systems for indoor farms. Dr. Sabeh has 20 years of experience dedicated to creating climate management solutions for indoor farmers and helping them achieve high productivity and profitability goals. Every design and recommendation made by Dr. Sabeh and the Dr. Greenhouse team is rooted in the discoveries of scientific research and the latest advancements in HVAC technology. She's authored the book Tomato Greenhouse Roadmap, contributed 2 chapters to the book Plant Factory, regularly speaks at conferences about climate control and HVAC design, and has been featured in and written articles for Urban Ag News, Greenhouse Management, Sun Grower, Cannabis Business Times, and Marijuana Venture Magazine, for which she also serves on the board of technical advisors. With that, I'd like to hand things over to Nadia. Take it away.
Hi, Aaron. Thank you so much for the introduction. Hi, everybody. It's nice to be with you today via webinar. So I have a lot to talk about as usual, so I think I'll just get started and talk about climate management and planning for it in your greenhouse or indoor farm. Okay, so we're going to briefly talk about why indoors, greenhouse versus warehouse or indoor grows, the added values of both greenhouse and indoor farming, planning and design factors, operational considerations. I will walk through a simple HVAC case study and then give you some final thoughts at the end. Okay, so why are we growing our plants indoors as opposed to growing them outside in a field? Well, there's a ton of opportunities, right? We can increase our yields and reduce our losses. We have more crop cycles per year. We can get more predictable and consistent quality and yields from our crop. We can steer the crop by managing different variables such as climate, irrigation, lighting, amongst other things. We can also use fewer resources. We tend to use less water in a greenhouse or in an indoor farm because we can spot irrigate, or we can irrigate as needed as opposed to just flooding a field or sprinkling a field, you know, when based on maybe the weather as opposed to measuring what the plant needs. We can reduce our operation and maintenance costs. We can manage risk because we now have our plants inside, and so if a hailstorm came through, if say you were in Colorado, the structure of your farm would protect you from that. There's not going to be any animals trudging through your indoor farm or greenhouse, most likely. And so ultimately, we're growing indoors because we are able to control quality much better by doing so. Okay. So, always a debate, right? I mean, this is an ongoing discussion, conversation within our community here in the cannabis industry, as well as indoor farming for other crops as well. And so here's just a general overview of what some of the advantages potentially are of each of these types of growing facilities. So with the greenhouse, the obvious thing, a couple obvious things are that we have a lower CapEx than a warehouse, right? So we need less structure, we need less light, we need less air conditioning typically. The building materials are cheaper, the real estate is usually cheaper because we're out in a rural environment. And because we're not typically using, say, air conditioning and a ton of high pressure sodium lights, we also get a lower OpEx associated with that. And the big one that everyone talks about is using natural sunlight, right? Is that there is the advantage potentially of capturing all the sun rays and all the spectrum of light from the sun without having to figure out what exactly the plant needs in terms of, say, UV or infrared or blue versus green. The sunlight takes care of all of that. We use less water than a field usually, and we're protecting the crop. With a warehouse, you know, we can grow anywhere, right? So Now, if you're in Canada or maybe Alaska, or you're in Arizona, or even if you're in a wonderful climate such as California where I'm located, you can grow in a warehouse. You can literally grow anywhere. And one of the reasons people like growing indoors is because we get much more precise climate control and lighting control, right? We're not reliant, or we're not so subjected to what's going on outside when we're growing in an opaque building. We can use light that's specific to the plants, assuming we know what that light intensity and spectrum is. We can reuse water inputs by collecting condensate, collecting runoff from hydroponics and reusing it. And we do get better containment than a greenhouse, right? So if we have a recirculating air system, we can prevent the loss of carbon dioxide. We can control odor much better if we're in an enclosed environment than if we're in a greenhouse using these big ventilation fans. And, you know, maybe it's better pest management. Okay. So the added value, just real quickly, of a greenhouse is that, you know, we can really hedge our risks against Mother Nature and market variability. So if you're growing in a greenhouse to grow something that is going to be wholesale, that's going to produce a product for extraction, right, you are hedging your risk against market variability, where the consumer changes their taste all the time. And so if you know that your product is just going to be for extraction purposes only, you don't have to worry so much about the trichomes, the colors, the taste, all of those quality characteristics, because you're growing something consistently all the time for one specific market, and you're not trying to guess where the market is going. Also, I would claim that there might be some advantages to variability. Maybe our plants actually do better under some stressful conditions. So having that precision of control in a warehouse seems 100% advantageous, but maybe our plants produce those trichomes, those colors, those odors, everything that we like about the aesthetic of the plant, because they're responding in a stressful way to those environmental factors that we are now controlling with precision to be the same every time. Now, the added value for an indoor farm is the potential for very high consistency, right? So if we are able to control all of those variables, the lighting, the irrigation, the nutrients, the climate, all of that, we have the potential to have a very consistent quality product all the time. And so we are able to meet our sales orders. We are able to meet a market demand as we need to. Another potential indoor added value is water use efficiency. So now we can actually use the air conditioning system to our advantage. So yeah, maybe an air conditioning system is very energy intensive, but if we can collect the condensate from removing that moisture through dehumidification and recycle it back into the system, we have the potential of using 90% less water than even a hydroponic system in a greenhouse. That's huge. So some prime factors in terms of planning and design of your facility. You need to think about, where are you going? What are your goals? What do you want to achieve with your crop? Are you growing clones? Are you growing flower for extraction? Are you growing flower for top shelf product? What is it that you need to do to accomplish those goals? Where are you located? That's going to affect the type of structure that you have. It's going to affect the market that you have. What are the design constraints and design criteria you particularly have for that location? And what's the associated return on investment and resource use efficiency? Okay, so I've already talked a lot about the crop and product and what your goals might be in terms of productivity. Location is key, no matter where you are, no matter what type of facility you're growing in, even if you're growing outdoors, right? You have to deal with a regulatory environment. You might have to deal with neighbors who are concerned about odor or about traffic or something like that. You have to think about distribution. How far are you to your market? What is the cost of real estate? Do you have the power you need to operate your farm? Right? Do you have natural gas on site to maybe reduce costs of electricity for reheat. And so thinking about what your site planning goals are, how you might want to expand and scale into the future, what your facility design targets are, and also how you're going to operate and manage this farm. Some things are out of your control, right? So rules and regulations, where you are, you know, even if you're just in California, California has a fundamental, right, standards of production, of facility design and operation, but then every jurisdiction is different. If you're in Sacramento County or you're in Kings County, that's going to be different, or even the city itself is going to be different. And so there's all these rules and regulations, size, canopy limits, visibility and security, odor control that you have to deal with your farm. You also have to think about your neighbors, right? We want to be good neighbors. This is one of the ways that we can actually help to legitimize and standardize this industry, the cannabis industry, into the mainstream, is by demonstrating that we are good people, we are good neighbors, we are not loiterers, we are taking into account the concerns of the people around us. And that includes, like I mentioned before, odor control, traffic control, and another one people don't think about is noise. If you have a bunch of air conditioning units sitting in, you know, in a commercial district, for instance, or even maybe a mixed district where you have commercial, residential, and industrial, are those people trying to sleep in the middle of the night going to be woken up by your air conditioning units running all the time, 24/7? And then, of course, utilities, and whether or not you have those utilities, and if your local utility is willing to bring you extra power, how much that's going to cost, and how much time that's going to take. And then some of the other sort of intrinsic, internal factors to think about are the local climate, right? So what kind of temperature and humidity are you dealing with outside? Do you have good solar radiation all year round that you might want to take advantage of with a greenhouse? Or are you somewhere very rainy and cloudy, and maybe it's better to be inside because you would have to supplement with light anyway in your greenhouse? What is your water quality, right? I talk to too many people who don't get a water quality report from their city to find out what they're starting with, and instead they take, I'm sorry to say this, the lazy way out, and they just stick a reverse osmosis system on the incoming water from even a good source of city water because they didn't get a water quality report, or they don't trust the system, I guess, so to speak. Pest management, right? So how do you plan to prevent pests? How do you plan to control them once you have them? And how do you plan to contain them also once you have them, so they don't get out, so they don't move to your next space, so they don't move to other facilities, even other growers' facilities. I'm always impressed when I visit a grower and they say, hey, we're dealing with such and such pests. We ask you not to go to, you know, another farm after you leave our facility because we don't want to contaminate them. That is the cannabis community that I love in a nutshell. And then just thinking in general about site development. So where is your growing facility located? Where is it located relative to the market, right? Where is it relative to other spaces that support your cannabis cultivation? So how do you move product from, say, a clone room to a veg room to a flower room to a dry room to a cure room to a trim room to a packaging room, and then out the door? That is a lot of steps that your plants have to see as they are growing and as you are processing them. So thinking about how you move plants from one room to the other room can really help you reduce the risk of contamination, reduce the risk of pests attacking your plants, reduce the risk of losing plants, and also reducing the risk of them being subjected to varying conditions. So I visited a farm where they literally moved their vegetating plants into a greenhouse and they had to walk outside to do it. And when it's 10 degrees outside and you move your plants from an 80-degree room to a 75-degree room, those plants, even if they're only exposed for 2 minutes to 10 degrees outside, they're not going to be happy. So some of the design criteria you might think about in planning your facility. Cost is always number one, right? Everyone's always obsessed with their first cost, their CapEx. More of you are considering your operating costs because as the price of our products are going down, we need to think more about how to reduce the inputs to our production facility. Precision of control. Do you want something simple? Do you love to tinker and you want something maybe more complex and innovative? How much time does it take to maintain? Do you want redundancy with your system? Is efficiency and sustainability important to you? And even, do you have a preferred manufacturer or a non-preferred manufacturer? Maybe you have experience with a certain type of equipment and you never want to use them again, and so you want to look for alternatives. All of that goes into what type of HVAC system you're going to install, as well as what your facility overall is going to look like. I talked a lot about design constraints associated with utilities and neighbors and building codes, but you might also have structural limitations, right? So if you find a warehouse that just looks perfect, but it can't hold equipment on top of the roof, that means we're limited to installing equipment on the ground. And that brings up other concerns. Okay. So greenhouses, just some special consideration related to greenhouses. So we have multiple different types of greenhouse types that are out there. I'm still partial to the conventional greenhouse design, which you would all be familiar with as having, say, you know, these big exhaust fans on one end and then maybe a wet wall on the other end, and we're evaporatively cooling the air before it enters the greenhouse. Some of you are probably considering a positive pressure greenhouse where you're air conditioning the space and doing a full recirculating system. And then there's also the hybrid greenhouse where you might have, you know, metal walls and a transparent roof. You're still air conditioning, but maybe you open up the roof vents at night for some humidity control, and also maybe to take advantage of some natural ventilation. So the structure for a greenhouse, there's a lot of variables or factors to consider when thinking about your greenhouse that you're going to build. Shape and size, of course. How big is this greenhouse going to be? Is it going to be an arched roof greenhouse? Is it going to be a gutter connected greenhouse, an A-frame greenhouse, a lean-to greenhouse? There's millions of greenhouses out there, right? What is going to be the cover on your greenhouse? How do you orient the greenhouse? Who is going to actually build and install the greenhouse and its components? And where are you going to get that greenhouse from? Who's the manufacturer vendor, or are you going to build to suit? So here's just a few examples of some different greenhouse shapes that are out there. And you can see even that they have different covers on them. So the ones on the left have a much more clear cover, so it's probably glass or maybe brand new polycarbonate. And the ones on the right, they look like plastic, and they are. The one in the bottom right is a combination of double polyethylene on the roof and polycarbonate structural walls on the sides. And you can see that that greenhouse also has natural ventilation available. So when you think about orientation and spacing, it's fun talking to the academics, some of the old guard in greenhouse engineering, and their thoughts on orientation. But I'm just going to present to you sort of the basic knowledge that we have. Look, if your latitude is less than 40 degrees, so if you're in Arizona, for instance, you probably want to orient your greenhouse so the long axis is facing north-south to help expose your plants to a consistent rate of solar radiation throughout the day and throughout the year. If Oh, that's funny. If your latitude is greater than 40 degrees north, you might want to do an east-west orientation, because now, especially in the winter, when you really want to take advantage of that greenhouse effect, the sun is going to be at a very low angle, right? So those of you who are in Washington or maybe Michigan know this, that when the sun is at a low angle in the winter, now you basically are sweeping the crop from left to right or from east to west with a consistent supply of solar radiation. And then thinking about shadowing. So if you have multiple single span greenhouses as opposed to a gutter connected greenhouse, you might want to think about shading and how to space those greenhouses so that as the sun moves, it doesn't inadvertently shade the greenhouse next to it, unless you want that. So glazing has been a hot topic with some of my projects recently, and the discussions usually range or fall around the percent transmissivity, so how much light, total light, or even PAR light is getting into the greenhouse. What is the spectral transmissivity? So a lot of the different glazings allow different spectrums of light into the greenhouse. In this graph, you can see that glass allows a good amount of UV radiation as well as a lot of infrared radiation. Polycarbonate, however, if you're just focused on the PAR, okay, which most plant scientists have been focused on PAR for so long, polycarbonate is wonderful. But what we're starting to realize is that there are a lot of benefits for UV radiation, even just a small amount, especially in terms of flowering and coloration and those tertiary phytochemicals that we're interested in, especially with the cannabis plant. And then you see ETFE. ETFE is kind of like a plastic cover. It was developed by NASA, and it has similar properties to, or similar costs to glass, but it has an amazing spectral range. And you also want to think about thermal insulation. So, you know, if we can have a double layer of something, it's going to have a higher R value than something that is single glaze. And so that's going to help prevent heat transfers in and out of your greenhouse. Sunlight. So depending on where you are, your daylight integral that your plants are exposed to is going to be different. Okay, and that relates to how much supplemental light and what type of supplemental light you might want. Honestly, I get really discouraged when I see greenhouse vendors proposing the same high-pressure sodium lamps for a project in Canada as they do in Florida. It is not the same, folks. The DLI, the amount of light that is produced in those two locations, is very different. And so, you know, just be aware that how much light and what type of light you provide should really be thinking about how much light your plant actually needs on a daily basis. And finally, I just want to say a thing about supplemental light. And so a lot of people, you know, are focused on high pressure sodium lights because they want a really high intensity discharge lamp. And this slide goes for indoor farms as well. But for those of you who are also growing vegetative plants, you might not need that much intensity in a 24-hour period. This is where DLI comes in, right? Is that DLI is the micromoles of light that a plant needs on a 24-hour cycle. What we know about a lot of flowering plants, and cannabis is a short day plant, means that really what you're trying to do, and you know this because everyone's talking about green light and whether we should do it or not, and is it triggering flowering, we want to control photoperiod, right? We want to prevent our plants from flowering, and that's why we extend the day length to 18 hours. If you can give your plants all the light they need in the first 12 hours, say, but you still want to keep the lights on for another 6 hours, use some really low intensity LEDs or fluorescent lights. and that's all you need for the next 6 hours. That will chop your energy bill by a third. Okay, so speaking of indoors, so we have a bunch of indoor models, right? A lot of you are starting to go vertically tiered, and that's really fun for me because I work with a lot of vertical farm clients, and so it's sort of the same challenges are associated with that. So there's a lot of types, right? Warehouse, container farm, and really what we need to think about in terms of the structure is the envelope. So, you know, do you have an open warehouse and you're insulating the warehouse, or are you insulating the warehouse? And also, or maybe you're doing a room within a room, right? Like the sort of the cold storage type of facility where you have metal insulated panels or structure insulated panels that have a vapor barrier and have a very high R value for insulation. And I would say vapor barrier is very important for your grow rooms. Lighting, right? So lots of lighting options. Layout is very important. So do we talk in terms of lamps per square foot, or do we talk in terms of plants per light? There seems to be, you know, a shift starting with lamps per square foot as opposed to being more obsessed with plants per light, which I think is a good trend to have. And people are starting to have a less dense lighting footprint than what I've seen in the past, which is great. Okay, so I already talked about DLI and photo period. Okay, so one of the special considerations, of course, with indoor farm is dehumidification. So we need to remove the moisture that those plants are putting out into the space. And so there's 3 general methods for doing that. One is a standalone dehumidifier, right? And basically that sits in the room and it's converting moisture into heat. And a lot of times that heat just gets dumped right back into the room. And so some of you who have indoor grows might experience those hot spots in the room where those dehumidifiers stand. The other way to do this is refrigeration. So now we have an air conditioning system, and as long as it's operating and it's cooling the air, it's sucking moisture out of the air that's passing across very cold cooling coils. And then we have desiccant, and now we're absorbing water to a solid or even a liquid media. So this picture on the right shows, you know, kitty litter. Kitty litter is basically desiccant. All right. So a thought on carbon dioxide. So when you're in a greenhouse and you're doing ventilation, you don't necessarily need carbon dioxide enrichment. I know a lot of you want carbon dioxide enrichment because you want to increase the production, the rate of production, and that's fine. But in a warehouse, you always need to enrich with CO2 unless you are ventilating your space and bringing outside air into your space. I've had clients who scratched their heads and wondered why their CO2 level, why their plants weren't growing. And we checked every variable, and I was like, you know, well, you know, you guys are enriching with CO2, right? Oh, are we supposed to do that? They went out and measured it with 220 parts per million. I was like, that's probably the reason right there. So when you have a very enclosed environment, you have to enrich with CO2 because that's your plant's food, basically. But what I want to say here with this graph is that the level at which you want to enrich with CO2 is very dependent on 2 other variables, and that's the air temperature as well as the light intensity. So if you're using very low light intensity, maybe you're using LEDs, I hope no LED manufacturers are on the phone, and maybe you're trying to control temperature to 70 degrees at the late stage of flower, pumping that room with 1,500 parts per million, your plants can't use that food. The metabolic rate is so low, there's no energy from light or very little energy from light. Don't pump your room 1,500 parts per million. Pump it with 1,000 parts per million because your plants literally just cannot use it and you're just wasting energy. Okay, so a few thoughts on just climate management and HVAC in general. So really what we're trying to do with HVAC is we're trying to control air temperature, humidity, CO2, air speed, leaf temperature. I don't have in here air quality, but that's also one of the things. And really, though, if you think about it, those are indirect measures. Those are indirect control variables to what we're really trying to get at, right? We're really trying to control the plant. So we control the air to control the plant. And so we're trying to control photosynthesis, water nutrient delivery, transpiration rate, the stress response from your plant, and those phytochemical productions. Climate management is a lot about controlling the stomata in your leaves and the evapotranspiration of water through the plant. Okay, so ET is evaporation, evapotranspiration is evaporation of water from leaves as well as other surfaces in the room, but generally speaking, it's mostly from the plant. Evapotranspiration is really responsible for moving water and nutrients from the roots through the shoots and the leaves. We're creating turgor pressure. So you have this low pressure that's in the room, and there's a lot of pressure of water in the plant itself, and so water wants to move from an area of high pressure to low pressure, and so water pushes up to the air where there's a lower pressure, and then simultaneously is sucking the water from the root zone, and the roots got their water through osmosis and chemical diffusion. But transpiration depends on the light levels, on the temperature and relative humidity or vapor pressure deficit, the stomatal opening, and if there's actually water available, right? So even if you have the perfect climate, but there's no water at the roots, your plants aren't going to transpire. They're probably going to wilt. So we have to talk about vapor pressure deficit. VPD is what drives transpiration. Okay, this is the pressure that literally forces water nutrients from the roots to the upper areas of the plant, as I already described. Okay, so it's the difference in the pressure of the air versus the vapor pressure at the leaf. And we think of the vapor pressure of the air as at the room temperature, where the vapor pressure at the leaf is really the vapor pressure at the leaf temperature, which, depending on how good you are at managing your crop, could be 2 degrees lower or 2 degrees higher than the room temperature. So this is a chart that we put together for determining what should be your target VPD levels at different stages of your crop. The green that you see is at vegetative stage. Yellow would be your normal flowering stage, and blue would be the last week or two of your flowering stage when you're trying to stress the plant. The vegetative column comes from a lot of research done on vegetating plants in general, such as lettuce and leafy greens, basil, things that never flower or that you don't want to flower, that stay just leafy. The yellow values come from our experience with flowering fruiting plants, so tomatoes, cucumbers, things that, even melons, things that produce a flower and then a fruit. We know like a VPD range of usually right around 1 kilopascal is what we target. For the blue, I've taken the blue from a lot of your experiences saying, look, we really want to stress the plant. When you want to stress the plant, you create an environment that they don't like, right? You flush nitrogen because nitrogen is food. You lower the temperature or the humidity because that creates stress. You do all these different things to create a stressful environment. And so this is, for me and my team and for many of my clients, this is our target. And I'm just going to point out that this is a very, some of these values might create some anxiety within some of you, because I know a lot of you are really concerned about high relative humidity numbers, but humidity is not necessarily the enemy. I know, we think of mold and mildew, and so we want to keep moisture levels down. But in fact, if your moisture levels are so low, your humidity is so low, and you have a stressed plant, just like when people are stressed out, our immune system goes down, and we can't fight off those viruses. We get the flu, right? We get a cold. We become more susceptible to diseases. Same with your plants. If you create a stressful environment when you don't necessarily want to, so during a normal stage of veg and flower, you are actually compromising your plant's immune system to fight off powdery mildew and botrytis. I'm not saying that you want a 90% humidity space, but don't be so afraid of relative humidity. And so what I'm talking about specifically is if you have a grow facility, say you're targeting 78 degrees, it's okay if your relative humidity is 70%. I'm sure that scares a lot of people. A lot of you are asking for 50, 55%, but again, that's creating a very stressful situation for your plant. Okay, so obviously there's no way I have time to go through all the different HVAC systems that I would love to talk about, but in general, right, we have cooling systems, heating systems, dehumidification systems, humidification systems, air distribution, air movement, which I have as 2 different bullet points, CO2 enrichment, and air filtration. If you're interested in learning more about these, I give these talks frequently and dive very deeply into these HVAC systems specifically, and so we can talk about those systems at another time, or I can share that with you later. So in general, when we want to select an HVAC system, there are certain design conditions we need to know to help you figure out what is the right system, what is the right size system to meet your budgetary and performance needs. So what's your location? What type of facility are you in? What are the construction materials? What kind of crop are you growing, or what stages of the crop are you growing, and how much of it is in each room? What are your performance, your climate targets? So what temperature and humidity are you trying to hit? And what are you trying to achieve when it's light out, when you have the lights on and when you have a dark period? Sometimes it's different. What are your sources of heat? Is it solar radiation, or is it high pressure sodium lamps, or is it LED lamps? All of those have a different impact on how your plants are going to transpire and generate moisture, as well as how much heat we need to remove through, say, an evaporative cooling system or an air conditioning system. Okay, so as promised, I'm going to do a little HVAC case study. It's a relatively simple case study, but I want to use it to illustrate a few points surrounding productivity and profitability as well as resource use efficiency. So all the time, right, growers are trying to balance the need or balance their budgets for capital costs and operating costs. So, you know, it's great if we can save a lot of energy in the future, but can we afford to install that super efficient piece of equipment today? And how much is it going to install? How much do I have to pay an engineer to design that system for me? Or do I just kind of want to figure it out myself and go to Home Depot or have a vendor just tell me what it is that I need? So I can maybe save on design costs because it's associated or wrapped into already the purchase cost of that equipment. In terms of OpEx, right, so you're thinking about the utility costs associated with that. You should also be thinking about the maintenance costs. If you install a piece of equipment that breaks down once a year, how much, well, first, how much stress is that creating for you, but how much time is it taking away from your day as a cultivator to grow your plant? Right? You have to make a bunch of phone calls. You have to get an engineer out there. If you have to sign, maybe you sign a service contract with someone. You have to wait for that equipment to be shipped and installed. And now it's not just a maintenance cost, but now it is an actual loss of productivity. Right? You've actually now lost a crop potentially or crop cycle because of that. So there are, you know, potential long-term ramifications of choosing a system that is cheap in the beginning. Okay, so real simple, again, a facility. So we have a warehouse, okay? It's 1,200 square foot production area. Actually, I think most people are now kind of in the range of 2,000 to 2,500 square feet of production area for, say, a single room. But again, you know, you could just double everything for the most part. So in this case, we're doing one plant per 4 square feet on a 60-day production cycle at the flowering room. The price is $2,000 per pound for the product we're going to sell, and the electricity cost is 12 cents per kilowatt hour. So real rough, you know, back of the envelope calculation, we need a 20-ton HVAC, or 20 tons of equivalent cooling and dehumidification capacity with our air conditioning system. Okay. So if we compare the two different systems, so maybe we have an off-the-shelf system. This is vendor supplied, or you went to Home Depot. It's something simple, right? Versus what I'm calling an engineered HVAC system, where you work with an engineer to actually go through all those design criteria and figure out exactly what system is going to be perfect for your needs and meet all of your expectations. So in the off-the-shelf system, maybe this system has 6 fan coil units that are ceiling mounted with 6 chiller type of units attached. The engineered system, on the other hand, is one packaged direct expansion rooftop unit, so kind of your typical air conditioner. It's ducted, but it also has dehumidification control. The efficiency actually is a little bit better with the engineered HVAC system, so that's good in terms of code compliance. You have temperature control, of course, with both. Your active relative humidity control. So with the off-the-shelf system, a lot of times you need to provide a separate source or method of dehumidification with those, maybe those standalone units, or maybe a different type of system that can do the dehumidification your air conditioner cannot do, especially when the lights are off and there's no heat in the space, right? The engineered HVAC system, we're going to choose something that has dehumidification control no matter whether the lights are on or off. You have, for the compressor, a single stage for the off-the-shelf system, and the engineered system is variable speed. That means that it's actually adjusting its operation based on the conditions in the room, as well as the set point targets you have set in the room. It is going to respond smoothly between those changes. There's no heating option on the off-the-shelf system. With engineered, you know, it might just be electric. Done. With the engineered system, you might have options with electric, natural gas, propane, hot water coils, diesel in some cases. The off-the-shelf system doesn't have heat recovery, but the engineered does, and that's probably why it has a higher efficiency rating. The fans, you know, we're not talking a lot about fans and airflow today, but there might actually be benefit to having variable speed fans in your HVAC system. We can have filters in both, controls, you know, onboard versus remote. And finally, if you look at the noise, so I did have a client who had installed a system like I described on the left, and the noise level, the decibels, were equivalent to 84 decibels. OSHA has a maximum limit of 85 decibels. At this level, your team, your staff, should probably be wearing ear protection. For the engineered system, what's interesting is that it's 74 decibels, but guess what? It's sitting outside. It's not in the space. So even at kind of a moderately to high noise level, your people aren't exposed to it because it's outside. And so then if you look at the purchase cost, oh my God, you know, like the one on the left, we have, it's $50,000, but the one on the right, and so $20,000 is maybe for the air conditioning, and $30,000 would be the additional dehumidifiers that you would need. So we're at $50,000, and then you have the engineering system. It's like, oh my God, $80,000 is almost 50% more the cost. Forget it, right? This is what a lot of growers do. They see that bigger price tag and it scares them. But now if we look at the operating costs, if we look at the longer term game, and the nice thing about this industry is that people aren't looking to, to sell their facility. They're not worried about the Fed necessarily coming in and shutting them down in 6 months or a year. Most people now are looking at a longer game, right? 5 years, 10 years. They want to be one of the producers forever. And so now if you think about the actual return on that investment of $80,000, all of a sudden it makes a lot more sense. So your operating costs of the off-the-shelf system, just that slightly lower efficiency, results in $6,000 more per year in your electricity costs. That's, also, in terms of revenue, actually these numbers I think are really conservative. When I talk to growers who have installed and engineered very reliable HVAC system in their farm, they're saying, oh my God, our crop losses, it's not 20%. Like, we don't have crop losses anymore. It's a savings of 100%. Your sellable product, that means your sellable product also goes up. The percentage of your crop that stays top shelf or stays the quality that you want it to, because there's no hot spots in the room, there's no stagnant air conditions. You are controlling the conditions exactly how you want. Sellable product and the value of that product goes up. So if you look in the long term in terms of first cost, electricity savings, maintenance savings, and the projected revenue adjustment or increase with the engineering system, your annual savings is, $8,500, and your payback is less than a month. This is a real number. So I really implore all of you, when you're thinking about, when you're weighing the pros and cons of different types of systems, think about what it is, again, you are trying to achieve. What is your goal? What is your end game? Can you live? Do you have the funding and the investment now to get the system that you want, that you need, that has a payback of well less than a year? There's also a bunch of added value for the engineering system, right? So now we have 1 unit as opposed to 6 chillers, 6 fan coil units, and I think, what did I have? 5 dehumidifiers. That's a lot of equipment to manage and maintain, right? Now you just have 1 piece of equipment sitting outside, it's not bothering anyone, and it's working all the time, and maybe you even have a service contract with it because the contractor you bought it from, is the real deal commercial contractor. You have combined temperature and humidity control. You can build in some redundancy, so maybe instead of 1 unit, you have 2 units that are sized together to serve that room, just to give you a little bit of safety factor. Better working conditions, better filtration. We have ducted air distribution, which means now we can put the air exactly where we want it rather than just dumping it in 1 or a few places and trying to use fans to circulate that air. We have this higher resource use efficiency, quick payback, and we're averting risk. And in terms of risk, everyone is always concerned about undersizing, right? I can't control humidity. My unit isn't big enough. But then what happens, actually, that's wrong. It shouldn't say frozen evaporator coilers. If you have undersizing, it just means that you're not going to be able to meet your loads, right? So your temperature levels might go up, your humidity levels might go up, and those are real concerns for sure. But the flip side of that is oversizing. And when you oversize, a bunch of other problems can happen, including poor control still. And because what a lot of times will happen is you will actually get these frozen evaporator coils in the room, right? Because it's trying to draw out heat when there isn't any heat because it's already pulled it all out because it was so oversized. But you're still asking it for it to stay on because you still want humidity control, for instance. The other thing is that you might get equipment cycling because it's so big. Now it meets the loads and then shuts off. It meets the loads in a few seconds and then it shuts off. And then it meets the loads and it shuts off, right? So you're overshooting your set points over time, and you're also going to increase the chance that you're going to have a failed system, right? Failed motors, and that it's going to burn out. You also, when you have a bigger system that you don't need, you're using more energy than you need, right? That's a bummer. And it also means that you're going to have to think about having a larger electrical service. So if you oversized your system, and if you had right-sized your system, maybe you needed a 50-amp service, but because you were scared of not having the right size, you oversized it, and now you need 80 amps. And now multiply that by 10 rooms, right? That's 300 extra amps that you need. That might be a whole new level of power supply from your utility. So I kind of want to end or wrap up here talking about energy savings opportunities, especially in terms of HVAC and climate management. So the first thing we talked about was structure, right? So think about your envelope. We want as tight of an envelope as possible, especially with an indoor facility and also a greenhouse. And so we prevent infiltration and exfiltration. That's air seeping through the cracks, right, of the building. If it's, you know, if you're trying to maintain a room temperature of 80 degrees and it's -1 degrees outside because you're in Michigan, all that heat that you're trying, you know, all that heat from your room is going to leak out into the outside, which is going to put more strain on your system and may even prevent it from being able to control your room set point. If you're in a greenhouse, think about coatings, right? So IR and UV, we talked about potentially the benefits of IR and ultraviolet radiation, but they can actually help to also reduce your thermal load. So if you have alternate sources of UV, or maybe you're just building a nursery for clones and you don't care as much about UV, that would be a great option. Use a polycarbonate or polyethylene greenhouse with UV and IR barriers and you're good. Think about the R value of, you know, which is insulation. So do you have a lot of insulation or no insulation? And I also mentioned vapor barriers. So I really recommend that you have walls and ceilings and even a floor that has a vapor barrier in it. I've worked with a lot of clients that had, you know, drywall installation with batt insulation between the wood stud framing, and they are never going to get rid of their mold because they had no vapor barrier, and once mold is in, it's in. Okay, lighting, right? So SMUD up here in Sacramento just recently did a study. There's a bunch of people who are starting to do these studies looking at the potential energy savings with LEDs versus high-pressure sodium and ceramic metal halide lamps. I would also put fluorescence in there. You know, there's a lot of traditional farmers who are growing leafy green type of plants who say fluorescence work just fine. So you want to think about power efficiency, and again, I'm going to bring up that topic of intensity versus photo period. Again, major energy savings potential there. Having an HVAC system that is designed, that has good efficiency, but also I want you to think about economizers. So specifically an air side economizer. I know a lot of you are nervous about bringing outside air into your space because you might be concerned about pest control, right? Or even about letting the carbon dioxide out once you've enriched that space. But there's a lot of energy savings potential with economizers, and even in some jurisdictions, again, going back to that idea of you might just be restricted by what your code requires, is that if you are have a space where you need 2,000 CFM of air or more, you might be required to install equipment with an economizer. And what that means is that if the outside air is the right temperature and humidity, you could actually bring in 100% outside air into your space to condition your room without using air conditioning at all. It's a huge savings if you don't have to turn on the compressors and you're just using the fan to blow air. But I will caution you that if you choose the economizer route, make sure that it has dew point control. If it's just temperature control, then that means that you might not be controlling or managing your humidity, even if you're managing your temperature. Energy recovery, so some of you are looking at combined heat and power. There's waste recovery would be another option for energy recovery. How you source your carbon dioxide. So, you know, as opposed to using combustion or even using expensive liquid CO2, which was probably produced from a source of combustion, what if you could just use a nearby boiler stack of CO2? So if you already need to generate hot water, or if you're near, you know, a plant that has large boilers or heat generating equipment, they're probably off-gassing CO2, and you might be able to pipe that to your facility. Renewable energy, of course, but usually the amount of power you need to run at least an indoor farm would require a very large solar field of photovoltaic panels. And you can just do some energy auditing. Ask your local utility or an engineer to come in and tell you, you know, some general strategies for saving energy with your building in general. So even if it's not crop specific, so like I talked about infiltration and exfiltration, right? So that's an energy audit. If you can go through your facility and look and see daylight under the door jambs, or where, you know, the walls come together, or where there's an old existing skylight, if you can seal that up, you're going to be surprised at how much energy you save. And you also reduce your risk of contamination, right? So the bottom line is that we want to maximize our outputs, right? While also simultaneously minimizing our inputs. Because ultimately our profitability is about revenue, right? How much money we bring in over how much money we put out in expenses. It's all about cash flow management, and ultimately we are trying to get our plants to respond in a way we want them to respond with using as little resources as possible, whether that's water or electricity or gas or even human power. So a couple final thoughts. Don't overlook the value of monitoring and controlling your space. You know, you can start simply by just putting temperature and humidity sensors in several locations within your grow rooms and spot checking them just to make sure things look good. You can also get more sophisticated systems that, that can alert you on your phone, or that you can dial into you know, the controller and see what temperature and humidity and light levels are in your space from anywhere. And you can also find systems that just do monitoring and just generate these nice graphics and these nice reports that you can use to help with your decision making as you go forward, in addition to alerting you when something is failing. I think this is my final thought, which is about facility planning in general. Again, thinking about workflow. How do your plants go from point A to B to C to D to E to out the door? Did you limit the plant's exposure to potential risks in doing that? How do you maybe want to think about space pressurization? If you have a warehouse where you have maybe a common corridor where you have a lot of different, you know, you have a clone room and you have bedrooms and you have flower rooms, how do you think maybe pressure might assist you with keeping contaminants out, or alternatively keeping contaminants in so they don't go into your production space? And lastly, I would say be aware of turnkey solutions. There is no one size fits all, kind of like I described with that greenhouse, you know, where they proposed the same high pressure sodium lights in Canada as they did in Florida. No, that is not a good design for you in Florida, probably, or worse in Canada if they gave you no lights. All right, so I think that wraps it up. I only gave 5 minutes for discussion, but I would be happy to take your questions.